I had a doctor's
Alright.
appointment in Boston this morning.
You rescheduled just for this?
Yeah.
So what I thought we'd do is look at some of the Berkeley tests and go over some of the stuff that is the new content mostly. But I wanted to start actually by showing a couple of really cool articles that I got this month's Communications of the ACM. People subscribe to this? You should join it when you're a student. It's like $39.
Yep.
And yeah, you're the only one or is anybody else? You should get this, Eric.
Is that a baby?
That's a baby and an iPad.
They had a picture of a cat using an iPad.
It's a baby using an iPad. But check it out. There's a cover story on Bayesian networks. So there's like, it's a whole overview of Bayesian networks. Let me see where it is. There, page, this is the picture associated with it, page 18. So, yeah, it's, oh, look, it's just like terrible lighting. Oh, here. Iris doesn't work. Oh, that's Iris. Close. Anyway. Yeah, so it's like 1, 2, 3, 4, 5, 6, 7, 8. This is a major article, 10, 11 pages. So I'll send that around, yeah. There will be some content on Bayesian network. Obviously, we didn't actually do anything with them, but I think we spent enough time thinking about them that we understand what they are. And also for Dana and anyone else who's interested in extracting information from text, did any of you guys come to Hannah Wallach's talk this semester in the colloquia? She gave this talk where she explained this stuff called a Dirichlet distribution, and there's a whole article on that. Where is it? I can't find anything. Here it is, topic modeling, page 16. Yeah, this is like the diagram that. So this is, it's latent Dirichlet distribution or allocation. It's like a recursion over distributions, probability distributions in multi-dimensional space. And this is a way of automatically doing, like if you have like a word distribution that represents a topic, a certain distribution of certain words in an article represents a topic being discussed. This thing will be a distribution over distribution. So it will actually abstract out topics even if you don't know what they are yet. So it's pretty cool. So this one, I know Dan would be interested in, and anyone else who's interested in this. This is not on the test. Latent Dirichlet allocations are not on the test. All right. So actually, since we don't have whiteboards, and you guys know that I love whiteboards, so we just use.
This one.
I know that's too small. It's pointless.
It's bigger than you think. Sorry about it.
Not really. It's not. No, I'm not using that. So let's just talk. I'll fill it up and then I'll get annoyed. So, and this way we'll also have a record of what we talk about. So. The big areas that we dealt with in this course are search. Thank you.
Yeah. Search.
Go ahead and scan these emails while I listen.
So that includes DFS, BFS, A-star, and UCS. I'm sorry.
Yeah, sure. DFS, depth first search, breadth first search, uniform cost search,
And A-star.
A-star. What else do we have? Is that all of them?
I mean, no, there's.
Oh, there's iterative deepening search. Yeah. And so then what were the biggie obviously is A-star. And what was the formula that summarized A-star? Yeah. And what are these, each of these things mean? You just did the A-star project, Darrell. I was right.
G is the cost from the start to a particular node, the actual cost.
Right.
And H is the heuristic, the estimated cost from that node to the goal.
Yep. Right, and then there's this concept of the fringe. And what does the fringe represent?
It's a priority queue.
Yeah, priority queue of what?
All these states, and the index in the queue would be their estimated value.
The index of the queue is the F function.
Yes.
Yeah. And what are some of the things about the fringe? What are some properties of it that you like or don't like? Or some good things and bad things about the fringe?
Well, if you have a lot of ties, it may be pretty hard to find the correct path to be where you're headed.
If you have a lot of what?
A lot of ties.
What do you mean by, oh, ties,
If you
like.
have a lot of things with the same
okay.
value, and you end up.
Yeah,
It's a list
did
of
that come
things.
up in your
Oh, yeah.
project? You had a lot of, that's right, I remember looking at yours now, you did a bar graph of
The number of ties.
yeah.
Can you say that again? Well,
If you have a lot of ties, you end up with more of a list of lists. So like each priority queue item is a set of equally valuable successor states that you could go to, and then you end up trying to tie break them, and that's a lot more difficult than if you're doing A star and every state you went through had a unique value.
Right. Eric's project was the Sudoku solver, and his fringe had a whole collection of elements that were basically in sets of equal, each set being an equal priority. So you expanded all the best ones. When you did that, did you expand, did you just pick one from the set of ones that were tied for the best, and then you expanded that, and then you go over the whole queue again and see which looks best?
Yes, so if there was one that was cheaper, it would expand that next, otherwise it would keep on expanding that cheapest one that it had just
Right,
expanded.
right. After you expand one from the best set, it could either be the new best, or it could be down in some other group.
Yeah, it could be, well, like, as many as 200 something successors if you're, on an empty puzzle, so it could be a lot more than one that you end up with, so you could have, half of them be cheaper, or...
Yeah, for people who didn't see Eric's, one of the things that I liked about it was he had a bar graph visualization as his algorithm was running that showed the distribution, like a histogram of the nodes in the fringe and what their value was.
Put it up there.
Yeah, sure, good idea. Okay. Yeah, so it was a nice live visualization of the fringe growing and shrinking. Yeah. Right, so here's his histogram. So these are the ones that look the best at the current moment?
It's actually popping off the one where the black line is, and
Okay.
that yellow little bar is how far it has popped.
That little
down.
tiny yellow dot there?
Yeah,
Uh-huh.
so it's almost done with that one.
Was there just one in that set right now?
I set a minimum height for it, so it wouldn't be invisible, but looks like there are maybe two in it, according to the little black status box that slides along the bottom with it.
Oh, okay.
So it says what the
Yeah,
estimated
the count,
value
it
is.
says count equals 2x down there.
Yep, so there are two states in that
In the-
that list.
Yeah. Yeah, that's nice. Why did you do this? Why did you make the distribution?
A little bit of debugging, and then as I was speed hacking it, I was like, hey, I can do this for free, and it's pretty cool. So
Yeah, definitely like a big part of the Berkeley problem sets was these tools that told us what was going on, like how big the fringe was, how many nodes were expanded. Right. So what's the biggest problem with A star?
find a good heuristic.
Okay, yeah, it could be a few things, right? yeah, problem space star. XR. Yeah, finding a good heuristic. Right, Keith, you also had challenges with that. What else could be an issue? You also had heuristic challenges.
Yeah, until I discovered that it wasn't possible to find one for the way I was doing it.
Did anyone else have A star in their project? Yeah, that's right. You had a lot of ties.
Yeah, but I think part of it was there was a when I was doing the write-up, there's the number of branches can actually go into the millions, like a certain step.
Wait, so your branching factor was literally millions?
No, I couldn't do it because it would just take forever, so that's why I selected just 15 of them. So I was doing A star, but on a limited set of nodes, so I was no longer guaranteed optimality.
Wait, so was your branching factor millions?
No, I couldn't do it. I mean, I could if I wanted to wait till, I mean, it was, theoretically it could be, but I just selected 15 random.
So for those who don't know, so Kareem's project was the course scheduler. So we'd look at what your degree program was, although it was hard-coded computer science, and what courses you've taken, and then it would make a map of what courses you should take for the rest of your undergraduate career. Why would the branching factor be millions? There's not a million courses.
I know, but if there's millions of combinations to take when you have like the gen eds or like you have 23 sections of English, like 42101 and stuff like that. So it's just
You're saying to, like, if you were to like do breadth first search and expand the whole tree, there'd be millions of nodes.
So the thing is, with XR, you need to have all those nodes there to compute, you know, the heuristic over all of them, and then pick the best one.
Yes.
So I couldn't do that because it would just take forever.
Oh, so as you're expanding, your fringe would literally grow to have millions of nodes.
Depending on what courses you've taken, the first step could be millions of nodes. Just not even the entire fringe, just the first step to have millions of choices.
How could the first step be millions of nodes if the first step?
Put all those things.
Isn't the first, wait, is the first step
Isn't it
the
like
next
choosing a
semester or
course?
the next course?
Yeah.
No, because a step is a course schedule.
Right.
Oh,
So
a
it's
step
all
is an
possible
entire
combinations.
schedule.
Yeah.
Okay.
So that was the problem. So I just and just the way I kind of software engineering.
Why isn't that a step? Why isn't it like a semester or a course?
It's a whole semester.
Oh, it's a semester.
Yeah.
Okay, so one step is looking ahead one semester.
Yeah. So it's a you have a single
Okay.
student schedule.
Okay. All right, and that could be millions.
Yeah.
All right. Yeah. Okay, so basically the big problem with A star is the whole fringe has to be in memory. So you created some simplification of the representation so that didn't happen?
No, I just picked 15 randomly.
So you also had lots of ties and you just picked randomly from like a bunch of
No,
ties?
it wasn't even a lot of ties. I just picked 15
15 what?
schedules.
And then,
That's it.
okay. Oh. And then how'd you decide which one to show?
Well, each semester, yeah. So then after that, we'd go through, with the tie-breaking stuff and just evaluate all of them.
Yeah, I had to do something similar on when I did. It's just like the number of possibilities grows crazy.
So that's like a general problem with search in general. Yeah.
I think you can see a lot of the chess stuff. It was just impossible to search all of them, so they have to make some kind of assumptions to whittle down the tree.
You know, that's one of the recurring themes in all of this stuff is the exponential expansion. But like in chess, which is not search strictly, it's the adversarial search. It's your branching factor is like a dozen or so, 13 I think is the number, right? So it's not like millions.
But
It's just that
it
as you go
quickly
down.
grows there.
Hmm?
It quickly grows into the.
Yeah, but you're saying that like each step in the search could be.
Well, yeah, mine would actually go down as you move along.
All right, let's go on to
That's
every.
those courses.
Let's do the quick overview of like the full set of things and dig into some problems. So adversarial search, let's do that next. So, okay, so that's basically the min and max algorithm. And then the thing that follows onto that is the alpha beta pruning. And we also looked at expectamax, which is the probabilistic sort of weighting. And other concepts related to this are the concept of there's a final state has a utility, like you won or you lost. But often you don't make your way all the way down to the final state. And then you have an evaluation function that computes sort of estimated value of current state. Did anybody actually do a version of adversarial search in their project? Yeah.
Yeah.
Right, you did.
In the Connect
Okay.
4.
Right, so Chris, his project was, he had two different methods of playing Connect 4. One of them was
One was minimax with alpha beta, which
Okay.
is considered the expert heuristic, and then the novice was a Qlearning one.
and then, again, for those who don't know, his project was actually pitting those two schemes against each other, and you were basically trying to figure out how well the Qlearning could do.
Correct. I
the-
did two tests. One was novice versus the expert to see the rate at which it would learn how to play the game versus an expert player.
And you defined expert as you coded up a minimax algorithm to play.
Correct, and I set the depth to 4 of the player's game moves ahead.
How did you know that it was actually a good player, the one that you declared to be an expert?
I played it, I couldn't beat it, but that,
Oh, really?
again,
Oh,
I could
okay.
be awful at it, so.
Is that like, is there published papers on like, here's, for instance, the evaluation function? That's usually the hard part, right, is figuring out the evaluation function.
Yep, with the evaluation function, easy enough to see if you or your opponent won was just if they were 4 in a row. But besides that, you had to take in consideration if there were 3 pieces with an empty spot in between, and if it could be reached, and all those other items, so.
Yes, but so the evaluation function, I think the way we did this in the Berkeley problem sets was some sum of products of like sort of feature extractions,
Yeah.
right? That's what we did with that?
Distance to food, distance to ghosts.
Yeah. So what did you use for your Connect 4 for the feature functions? So like 3 in a row is a good thing?
Yeah, well, 3 in a row, 3 in the space of 4 where the spot in between was worth the value, so that a 4 could be achieved.
Okay.
It's not just 1, 2, 3, and then the last one's always the last piece.
Because
It
it's
could be the
blocked, it
second,
doesn't
third.
help you.
Correct. So each one of those were different values. If you had 2 in a certain space, it was worth somewhere around 10 points. 3 in a certain space was about 100, and basically the thing was is that if they compounded over the entire set, that a 3 in a row would still show up better than a bunch of 2 in a rows.
Where did you just make those up, or did you like do some lit review and find those?
Made them up. It seems to work.
Right, so what is another aspect of the feature functions in order to make this viable in a real like application? What must be true of the feature functions?
We have to reward states that move closer to your goal.
Yeah, so so the overall, the sum of a bunch of them with different weights should actually represent a good state. Yeah, right. So well, and a lot of the playing around is what's the right weights. But you also did a feature function thing with your Tetris
We
game.
didn't want to figure out the weights, we made computer
Right,
for
your
us.
thing was about learning the weights. So, but what's one of the characteristics of the actual implementation of doing feature functions. That's a necessary requirement for this all to work out in practice.
Just like world knowledge.
Oh, well, that's going forward. It should be easily computable. Right? If one of your feature functions entails a whole search process, that's usually not going to work out in practice. I mean, theoretically, okay, but in practice, it has to be easily computable. What were you saying, Kareem?
Well, you have to have like world knowledge. You have to know where all the ghosts are and all the dots are. You can't just have local knowledge. You have to have knowledge of everything.
Right. With search and adversarial search, the assumptions we're working under is the world is fully observable. That's like sort of a fundamental assumption.
Is that a requirement?
Let's think about that. Could you do a search if you don't really have full sense of the world?
Well, you can't do an A* search. That's kind of the problem that I was having originally, because if things are changing from under you, then the decisions you made early may not be accurate anymore.
Yeah, that's right. Yeah. Right. If the world is changing as you're trying to find the best way through it, then your plan is going to be wrong. Yeah. Right, well, the whole sort of second set of content was about partially observable worlds and worlds that change as you make moves and all that. Yeah, this is sort of the simple world assumption. All right, let's keep going, and then we'll circle back and look at some like test questions. Okay, so the next big set of things we did was markoff decision processes. And, all right, you want to find my notes to go back to the formal description of what's in the Yeah, we did like value iteration and Qlearning were the big techniques that we went over. So it's all good. Does anyone have notes handy on what was like the definition of a markoff decision process? I'll find them. Here we go. Okay, so we have a world that has a set of states. So little s is one state and it's an element of the full set. We have actions, and an action, there's a set of possible actions. We have a transition function. It's all coming back now. Transition function goes from a state and an action to a new state. And there's some probability associated with that. Like it might not always happen. When you're in state S and you take action A, probabilistically you will end up in S prime. And then there's a reward function. So when you make one of these moves from state S, given action A, and you end up in S prime, then you get a reward, and you could also define that as just a reward for having entered a state. There's a start state, and there are one or more terminal states, maybe. And then there's this idea of a Q state, which comes in the Qlearning, of course. And a Q state is a state action pair. so what do we do with this? We defined this idea of utility. And what an utility is a sequence of rewards. Going from state to state to state. And then we introduced this notion of discount. So probably rewards in the future are worth less than, like, money in your pocket is better than money that you'll probably get later. That's the idea there. So the utility of a series of rewards, R0, R1, R2, and so on, is defined as the utility of R0, the reward R0 plus, and then there's this gamma discount factor times R1. The reward for the next day, and then gamma squared times R2, and so on. And gamma is, I just can't write gamma. It's greater than 0 and it might be 1. If gamma is 1, then there's no discount. Okay. So then we also have this notion of a policy. A lot of the work that we're doing here is trying to figure out the policy. But the policy is, we write it as pi, and a policy is an action for each state. And there's a definition of the optimal policy, which maximizes utility. And then there's a notion that if you have this policy and it's fixed, it basically, a fixed policy implies a reflex agent. So the first thing we did in this problem set was we did value iteration to determine the best policy. And if you remember, like, running the code, there was this, like, value iteration thinking step up front, and then it said, here's the policy, and then the agent doesn't think anymore. It just, like, looks up, I'm in state S3, I should look at my policy, and it will tell me what to do. No more moving at that point. Chris, can you talk about, like, so when you did Qlearning, you ended up with a policy, right?
Yes.
And how did that factor into your, like, overall project design of your novice trying to learn a good policy and then play against the expert?
All right. So when it was playing, to learn the policy, I'd run through several thousand training meetings, and basically what it would do is it would either play the expert or a copy of itself, which would learn at the same rate. So it would keep building up the policy, build up the policy, build up the policy, so that at any given game state, if it had a board that matches one in its policy, it would take the best move from that state, given what its prior knowledge had been.
So, all right, so your Qlearning agent is playing whichever it's, you know, a copy of itself, or playing the expert, which is playing different. It's playing an opponent.
Yep.
So it's got a board state. So your board state represents one of our states in this like model here. So the state of the board with a collection of pieces played is an S.
Correct.
Okay. And then its actions are, it has 7 actions.
Yep.
Up to
All
7,
open, that's up to 7.
dropping its piece in any of the 7 columns unless one of the columns fall. And so then how does it know, how does it figure out the utility of one of those actions? So basically it's in a state, it has up to 7 choices. Presumably each of the 7 choices will ultimately have a different utility.
Yeah, they have a different utility. I use the same value function that I did for the expert heuristic for minimax to determine the board value given what it would achieve at each state.
Okay, so it had the same like weighted sum of feature extractors to determine.
Correct.
How is that Qlearning then?
Maybe I'm saying it wrong. 1 second.
Yeah, let's look at the. Why don't we hold on to that thought? Come back
Okay.
after. Let's look at Qlearning. Well, I guess we should do value iteration first. All right, let's go back to the value iteration. All right, so we'll come back to you, Chris.
Yep.
All right, so there's the Bellman equations. Sorry? Oh, too high. Okay, so the idea is optimal value. All right, well, this first equation is not that difficult. The value of a given state, the best value of a given state is you look over all of your actions and you take the Q value that's the highest over all of those actions. So you iterate through, in the case of the Connect 4, you've got 7 columns, you look at which of those actions gives you the best value, and that's the value of the state you're in. You always take the best choice. But that sort of buries the interesting part in what's the value of a state action pair. So here's the Bellman equation. All right, let's see if we can get this. So it's the sum over possible places you'll end up. The transition likelihood of ending up in that place, given that you try to get there, times, I'm just going to, this is going to be the product here. The reward for getting there, plus the discounted utility of being in that new state. So here's the recursive part. So you iterate over all possible states you might end up in, and for each of those states, there's a likelihood of getting there, and then the reward for getting there plus the recursive value of being there. Chris, did you influence something like that?
Yeah.
Okay, all right, no, that's fine.
For the Qlearning, I was using the
This is-
unmodified version of the Pacman code.
Okay, oh,
So
right.
It,
So you
it
just-
does have the value function, the randomness, and the other items that to explore the board and such.
All right, hold on, Chris. Let me. I know I'm just pestering you basically, but hold on. So this is still, we're still on Qlearning. So now from the Bellman equation, we can do value iteration, which again is the static computing what is this state worth, assuming you're not learning anything as you go along.
So that's policy?
Yes, this will give you a policy. I mean, when you're done with value iteration, you have a policy. So the iteration step, so the V of I plus 1, that's as you're computing the values of states, as you repeatedly apply this formula, you're repeatedly calculating the value of each state, so of a given state. So that one gets the max over the action. So here's where you always pick your best choice. And now it's just going to be basically that formula again. It's the sum over it. I'm not going to copy it. It's just that thing again. Well, okay, not exactly. It's almost that. Alright, it's, alright, so it's the transition likelihood of, if you choose the action in question, getting to the S prime state. There's just one slight change of formula here. The reward of getting an S prime plus the discounted utility. Here's the change. Here's where we've already calculated what we think the value of being in S prime is in the ith iterative step of value iteration. So we're recomputed. So we think we already know what S prime is worth from the last time we did this. But as we go through all the states, we calculate a new value for each of the states. But each time through the iteration, we include the discounted value that we believed last time. Okay, so that's value iteration. So now let's look at Qlearning. Does anybody have a notes handout on Qlearning I can use? I might eventually find this.
I do Fred.
Oh, great.
Maybe.
I might like borrow that and then give it back. Yeah, this is it. Thank you. Okay, all right. Yeah, thanks for that. All right, so why are we doing Qlearning at all? Does anyone remember? Okay, it has to do with what do we know and what we don't know. So I'll go back to our definition of a Markov decision process. So here's the definition of MDP. So the reason we would do Qlearning is we don't know some of these things. In particular, we might not know what the transition function is. Nobody told us what the likelihood of, if we're in a state, we choose an action, we don't really know what's going to happen. So we don't know that. It's not given to us. And we also might not know the reward function. We might have to discover that. So the idea of Qlearning is the idea of Qlearning is we play the game and we get rewarded when the game ends, and then we figure out progressively what different states are worth. And actually finally we don't necessarily have a separate representation of the transition function or reward function. We just know that given a certain state, we can make a move that will yield a certain value. So the summary here is we don't know the probability or transition functions or the reward function. So basically what we do is we'll just like play the game. The game is we're in a state and we have actions. Yes, it's all coming back now. And what we're trying to do is learn the optimal policy. Right, so just like value iteration will finally give us an optimal policy, but here we're learning it directly. And the learner makes choices along the way. And then the learner can trade off what? What can the learner trade off as the learner is exploring the space?
Can take chances.
Yeah, yep. What does it mean, take a chance?
Take a random.
Yeah, it move randomly. That's one way of implementing taking a chance. Okay, what's the,
It means exploring versus taking the known.
Yeah.
Yeah.
that knows.
Yeah. Exploiting is the term for doing what you already know. Right, so the idea here is if you're exploiting a known path, then you've got some confidence that that path will yield a certain value, reward at the end. Whereas exploring is you're taking a path that you haven't taken before and you don't know what's going to happen.
There's some probability that you're going to do that.
Right, so that could be, we modeled that as just some simple like likelihood that you will either explore or exploit. There's some factor, it's not in these notes, but yeah, basically it was just some probability that you explore or exploit any given step. Oh, epsilon. Yeah. So you say if yeah, epsilon is the random, you choose an epsilon, then 1 minus that epsilon is exploit.
Probability of exploiting? Or
Uh,
yeah.
Yeah, so, right, so if you set epsilon to 0.9, and this was a command line parameter of the simulation, right? If epsilon is 0.9, then 0.9 of the time it will choose randomly among actions, and 0.1 it will exploit known paths, which exploit means pick the best action. Like you've got some, you've done, Qlearning is operated for some amount, and given your state and your set of actions in the state, you've got expected rewards based on the Qlearning that's already happened, and if you exploit, you just pick the best one, because, well, what you pick the best one. Okay, so the update equation for Qlearning is very similar to the one for value iteration. What's that?
You just couldn't read it right. After the verses, it says E.
Oh, epsilon random?
Yeah, random, that's
Oh,
just
random.
random, sorry. I knew I was running out of room, so I wrote it down. Okay, so the Qlearning algorithm. So basically what we're doing here is we're going to be learning the, for each state action pair, we're going to be learning the best choice. And the way we're going to do this is we're going to receive a sample. So this is what playing the game is. We're in a state, we choose an action, we discover that we arrived at a new state, which, by the way, that could be the same state. Remember that there are some actions that you try to go north and you're running into a wall, so you end up back in that same state, probabilistically. And then you get some reward for having done that. So each time you play the game, you get one of those tuples. And then what you want to do is update, you've got some previous estimate for what you think the value of that that cube value pair is worth, and then you update it based on that knowledge. Okay, so here's the formula. So the optimal value of a state action pair, sum over the possible resulting states. Wait a second. This is going to be like assuming you already have T and R. All right, well, let's write this out and see where it goes. What happens if you don't have this? Here, that's the max over your possible actions.
Is it A prime?
Sorry?
Is it A prime?
Yeah, A prime.
What? What's A prime?
It's the action you actually take.
Yeah, let's think that one through too.
I'm sorry, what's R again?
R is the reward, but we're sort of, yeah, there's something missing here because we don't really have the T and R. This is, so, but this Q star is the state you end up in. So I think, Eric, the A prime is not the, it's not the action you actually take, it's the action you'll take next time. So, I mean, this is just like this is the Bellman equation where this is the state you end up in and the expected value of that. I mean, you know, this is basically, it's a recursion to the same formula, but you've got A prime here because you're in a new state, so there's another set of actions to max over.
In the slides from the MVP lectures, it actually uses V star instead of the max action for Q values in that given state. So if you would pass the S prime in, it just finds the maximum action for all the actions in that state.
All right, let's go find those. Wait a second. I posted these, didn't I?
I think it's under Tuesday, October 12th. In the lecture blog.
No, sorry, I thought it was in the lecture blog.
It's like slide 17-ish.
Okay. Slow computer. Let's try and. Yeah. This is still value iteration though, isn't it?
Yeah, just saying that with how they defined it, the action has nothing to do with what action you actually take. It's just the actions that you could take from whichever state you pass in.
Yeah. All right, let me go. This is where the Berkeley content and the book, the presentation slightly differed. So that equation at the bottom of the slide, and switch to what I wrote down here. I mean, it's the same story here. This is the value of the next state with a gamma discount factor. I mean, it's the same thing, it's just written slightly differently. But I think we're still trying to find the Qlearning story. In Qlearning, you don't have, yeah, that's the value of, the optimal value of that state you end up in. which again could be the same state you started in, because your action might not lead you to a new state. Let's see if, okay, in here, if we've got, yeah, so we're still in value of iteration. Yeah, this set of slides doesn't deal with Qlearning.
So is this final completely on everything that we've covered in the class?
Yeah,
Okay.
I don't think anyone's having a problem with the first, the first two chunks of content, because people did really well on the quiz. But, if there's 3 hours, I'm gonna use them up. I have to grade them, so it's not like,
People did well, should you have more questions from there? A lot of professors seem to take the hour approach. I mean, that seems something that'd be good for everyone.
It's a good point, they do that.
Plus,
but then that wouldn't be
last
fair
line.
to students who did badly on the quiz. They should get a chance to prove they've learned the stuff that.
You can wait it more, you just don't have to. They can take the extended. Qlearning says if they did bad on
Just
it.
give us 10 questions, say pick one. Or pick two.